Good morning. Today let us see analog to digital conversion. The process of converting an analog voltage into an equivalent digital signal is known as analog to digital conversion. There are two methods for performing this. The simplest method is simultaneous method. It is also known as flash type A to D converter. This converter is constructed by using comparators, coding network, flip-flops and reference voltage sources. Comparators are used to compare the input analog voltage with that of the reference voltages. The number of comparators for converting analog voltage into n-bit digital signal is 2 power n minus 1. To get 2-bit digital output, we require 2 power 2 minus 1, 3 comparators. To get 3-bit digital output, we require 2 power 3 minus 1, that is 7 comparators. 3 reference voltages plus V by 4, plus 2V by 4 and plus 3V by 4 are used in a 2-bit converter as one of the inputs of the 3 comparators respectively, which are then compared with the analog input voltage given to the other inputs of the 3 comparators. In a 2-bit converter, there are 3 comparator outputs which have to be converted into 2-bit digital output. For this, coding network is used which has 3 inputs and 2 digital outputs. The digital outputs are stored in flip-flops. One flip-flop is required for 1 bit, and so in a 2-bit converter, 2 flip-flops are used to store the 2-bit digital output. The block diagram shows a 2-bit simultaneous A to D converter. It makes use of 3 comparators. From the bottom, the first comparator, one of the inputs is the reference voltage plus V by 4 and its output is C1. For the second comparator, one of the inputs of the comparator is the reference voltage plus V by 2 and its output is C2. For the third comparator, the reference voltage is plus 3V by 4 and the output is C3. The outputs of the comparator C1, C2, C3 are given as the input for the coding network, and the 2-bit output of the coding network is stored in the RS flip-flops as 2 power 1 and 2 power 0. Whenever the analog input voltage is less than the reference voltage, the comparator output will be 0. Whenever the analog input voltage becomes greater than the reference voltage, the comparator output will be 1. So starting with when the analog input voltage is less than plus V by 4, all the comparator outputs will be 0. C1 is equal to C2 is equal to C3, which are 0. This is shown in the first row of the truth table. Whenever the input analog voltage is greater than V by 4 but less than V by 2, the first comparator output will be 1, other two are 0. So C1 is 1, C2 and C3 are 0. Whenever the analog input voltage is greater than V by 2 but less than 3V by 4, the first two comparator outputs C1 and C2 are 1, C3 is 0. Whenever the analog input voltage is greater than plus 3V by 4, all the 3 outputs C1, C2, C3 are 1. This is shown by the last row in the truth table. Now, the coding network outputs, we have 2 outputs, 2 power 1 and 2 power 0. These outputs are written here. Since it is a 2-bit data, we have 4 possibilities: 0, 0, 0, 1, 1, 0 and 1, 1. Now we have to construct circuit for 2 power 1 and 2 power 0. This is the truth table for 2 power 1 and this is the truth table for 2 power 0. We can use sum of products method, or we can use some logical methods to write the expression for 2 power 1 and 2 power 0. In this slide, the same truth table is rewritten. Low stands for 0 state, high stands for 1 state, and the truth table for 2 power 1 is here, 2 power 0 is here. Using sum of products method, we can write the products for high output as shown in the table, and 2 power 1 can be written as C1 dot C2 dot C3 bar plus C1 dot C2 dot C3, which can be reduced by using Boolean algebra as C1 dot C2. Similarly, you can write 2 power 0 is equal to C3 plus C1 dot C2 bar. This expression for 2 power 0, it can be written by looking into the truth table. In the truth table, the 2 power 0 is high for the state which corresponds to C3 of this input values. So it can be written as C3 plus. You have another one high state. For this, the expression can be written as C1 C2 bar, because C1 C2 bar will be high only for the second state. For other states it will be 0. So 2 power 0 can be written as C3 plus C1 C2 bar. The corresponding circuits are drawn below here. Instead of writing 2 power 1 is equal to C1 dot C2 by using sum of product method, we can compare the output of 2 power 1 with the inputs C1, C2 and C3. We can see that 2 power 1 corresponds to the input C2. So instead of using AND gate for 2 power 1, we can directly give C2 to 2 power 1. The circuit will be a simplified one. Next we will see 3-bit simultaneous A to D converter. The number of comparators required is 2 power 3 minus 1, that is 7. Reference voltages are V plus V by 8 plus 2V by 8 plus 3V by 8 plus 4V by 8 plus 5V by 8 plus 6V by 8 and plus 7V by 8. The coding network has 7 inputs and 3 outputs. This is the block diagram for 3-bit simultaneous A to D converter. And as we explained for 2-bit simultaneous A to D converter, here we have to explain the outputs of the comparators when the analog input voltage is compared with the reference voltage. The outputs are given to the coding network. There are 3 outputs for the coding network because it is a 3-bit simultaneous converter. These 3 outputs are stored in the 3 RS flip-flops respectively, and the outputs of the RS flip-flops give you the 3-bit digital information. Whenever the input voltage analog signal is less than V by 8, all the comparator outputs will be 0. Whenever the analog input voltage is greater than V by 8 and less than V by 4, C1 will be 1 and other outputs will be 0. Whenever the analog input voltage is greater than V by 8, 2V by 8 or V by 4 and less than 3V by 8, C1 and C2 will be 1, other outputs will be 0. Whenever the analog input voltage is greater than 3V by 8 but less than 4V by 8 or plus V by 2, C1, C2, C3 will be 1 and other outputs will be 0. Like this, we have to compare the analog input voltages for all values below plus V by 8 and above plus 7V by 8 and write the truth table connecting the comparator outputs. Here the input voltage levels are given and corresponding outputs are represented as C1, C2, C3, C4, C5, C6, C7. Here again low stands for 0 state and high stands for 1 state. And the coding network should convert these comparator outputs into 3-bit digital information, 2 power 2, 2 power 1 and 2 power 0. So we write the possibilities for 2 power 2, 2 power 1, 2 power 0 below. Since there are 3 bits, you have 8 possibilities. So the 8 possibilities are written in this ascending manner. Now we have to construct circuit for 2 power 2, 2 power 1 and 2 power 0. When you see the outputs for 2 power 2, this output resembles C4. For C4, for the first 4 states, the outputs are low, and for the next 4 states, the outputs are high. So here, this is similar to 2 power 2. So you can write 2 power 2 is equal to C4. Then when you consider 2 power 1, 2 power 1 is 1 for the last 2 states and the third state and fourth state. For last 2 states, C6 is high. So you have to write C6 for the last 2 states. For the third state and fourth state, no comparator output is high. So you have to find the combination of 2 outputs. So for these 2 states, you have to consider C2 and C4. If you write C2, C4 bar, C2, C4 bar will be high only for the third state and fourth state. For the other states it is 0. So 2 power 1 can be written as C6 plus C2, C4 bar. In the same way, you can write 2 power 0 for this one state. It corresponds to C7. So C7 plus. For this one state, we have to write C5, C6 bar. Only for this level, C5, C6 bar will be high. Otherwise, it will be 0. Then for this one state, it is C3, C4 bar. For this one state, it is C1, C2 bar. So you can write 2 power 2 is equal to C4. 2 power 1 is equal to C6 plus C2, C4 bar. 2 power 0 is equal to C7 plus C1, C2 bar plus C3, C4 bar plus C5, C6 bar. For these expressions, we have to construct the coding network. This is the coding network corresponding to the 3 digital outputs. Then the outputs are given to the RS flip-flops through the read gates and stored in the flip-flops. The flip-flop outputs are the required 3-bit digital output. Next we'll see the second method of A to D conversion. It makes use of one comparator and a binary ladder. The binary ladder is a D to A converter. So counter type A to D converter makes use of D to A converter and the comparator. The comparator, one of the inputs of the comparator is the analog input voltage. Another input is the reference voltage. The comparator compares the analog input voltage and reference voltage and produces an error signal. The error signal is given to the gate and control circuit. To the gate and control circuit, a clock generator is connected, and the gate and control circuit controls the clock signal from the generator to the counter. The start pulse initiates the working of the counter, and the counter of output is given to the level amplifier and then to the binary ladder. The binary ladder output is nothing but the analog output, which is considered to be the reference voltage. The input of the binary ladder is taken as the digital output. If you have n lines in the binary ladder, then these n input lines are taken as the digital output of the A to D converter. To start with, the counter is reset and all the outputs of the flip-flops in the counter is 0. So the reference voltage is also 0. Now you give the analog input voltage to the comparator. Whenever the analog input voltage is less than the reference voltage, the comparator output will be an error signal which will be opening the gate. When the gate is opened, the clock signal goes to the counter through the gate and the counter starts counting. When the counter starts counting, the reference voltage increases in step. So the reference voltage is nothing but a step voltage. When the analog input voltage is greater than the reference voltage, the error signal produced by the comparator will be closing the gate. In that case, the clock signal will not go to the counter, so the counter stops counting. When the counter stops counting, the n input lines of the binary ladder corresponds to the digital output corresponding to this analog input voltage. So this is a method which makes use of a binary ladder and comparator, and the advantage of using this method is it is enough if you use only one comparator. Whether you want to get 2-bit output data or 3-bit output data or n-bit output data, we require only one comparator. Thank you.